Hi and welcome. I'm trying to learn electrical engineering today, potential difference, and after we've done it, we're going to do leg injury prevention training. And if you participate in the leg injury prevention training, then it's very harmless. Potential difference. When a current flows in any conductor, a potential difference exists between the ends of a conductor. Okay, I know already that current means electricity basically, but it's just the term we're using. Current is basically electricity coming in. So electricity or current flows in or whatever, in something in a conductor. A potential difference exists between the end of a conductor. Basically we're saying if electricity comes in somewhere and at the other end out, there's a difference. Something was lost. I think we have understood it. At least the whole thing. This, now P and the T, I don't know what P and T means. This a potential difference. This potential difference is measured in volts, usually by placing a voltmeter across the ends of a wire. Okay, the first thing, it is measured in volts. So what is lost there, like a river can lose something on the way, or a pipe having a leaking, there's current, so electricity coming in, current comes in, and at the other end of a cable there's less, of a conductor or whatever. And now what is lost do we measure not in liters of water lost, but in volts of current or of electricity lost. Volts it lost so much current was lost in so much volt. And it is usually done by placing a voltmeter across the ends of a wire. Now, first, what is a voltmeter? I don't know it, but let's say it's a little box and it measures something. And it is used by placing this voltmeter across the ends of a wire. I don't understand what I mean. Whatever, let's just say we're measuring what is here, comes in and what comes out, and the difference is measured in volt, and that was done with a voltmeter measure, and now we know the potential difference between the potential which this current had here and it has now here. Neither the current nor the potential difference will exist unless somewhere in the circuit concerned is a source of electrical energy. Let's do it again. So neither the current nor the potential difference will exist. Cannot be a potential difference if there's no current at all. Okay. The current can exist, and if it exists and comes through a conductor, then there is a potential difference. And now if they both exist, then we have now the opposite. If they don't exist, neither the current nor the potential difference will exist unless somewhere in the circuit concerned is a source of electrical energy. I understand it that way. If there's not someone doing energy, then there is no energy. There is no electricity or no current. Okay, someone has to put the current in so that it comes out, can be measured by voltmeter and volts. This will usually be either a generator which converts mechanical energy or a cell which has a store of chemical energy. Okay, we first need to generate our current or electricity. And we're saying by mechanical energy, so we're taking a dynamo or something turning, and that somehow does electricity. We had that in the previous part, in electrical engineering. That was something turning, and on the outside there's wire, and now this difference makes somehow electricity because there's a magnet turning inside of a wire of metallic wire. So through mechanical energy there's something turning, or through a chemical energy, whatever. We're just saying we have to generate our electricity or our current. This source of electrical energy is said to have an electromotive force measured in volts, which is the total driving force available to push a current through each component in the circuit. So let's look what we have here. So this source, whatever, something generating is, of this electrical energy is said to have an electromotive force. No, that's that one. It is measured in volts. That makes sense. So what is lost in current is measured in volts, and also now the electromotive force of this electrical energy which we have generated is also measured in volts. That makes sense. But we're measuring them all in the same. And which is the total driving force available to push a current through each component in the circuit. No, just at the side, there's actually an amount of energy necessary to push the electricity or the current through the wire or through the cable or whatever. What is this? Maybe it's not true. So what did we say here? I understand it that way. This current has to have a certain amount of this electromotive force which pushes it actually through the wire. I'm taking again the water example. If there's no pressure on the water does not flow through the pipe. Okay, That is measured also in volts. So far so good. The resistor through which a current is flowing. Voltmeter measuring potential difference across ends of resistor. The V is for voltmeter. A voltmeter. The V is for voltmeter. So V is for voltmeter. So, yeah. Mixed up. Let's look at 1 second. What is this thing here? An ammeter, a cell, or whatever. Resistor through which a current is flowing. Voltmeter.
Now I understand it that way. The electricity of the current is flowing from here to here, just peacefully, and when that thing measures what was here and what is here, and the difference is the potential difference. And it goes there through something, whatever.
Through the resistor. And that makes resistance, and this resistor has taken something off our current. And I'll be measuring at the beginning and the end the difference. And that is the potential difference. It is often difficult to know when to refer to a potential difference and when to refer to an electromotive force. Both are measured in volts. Considering of a simple circuit may make the distinction clear. Maybe we're going to have another example. Let's still try to, if you get it. It is often difficult to know when to refer to a potential difference and when to refer to an electromotive force. Because, no, let's not speculate that much. Now, what do we have here? We have some type of circuit. We have an A, and A is an ammeter, whatever an ammeter does. Then we have an Y and an X. It's not explained. And when we're having 3 resistors, A, B, and C. And the potential difference of the first one is 3, 2, and 4. And if the switch is closed, then let's try to read the text. The potential difference across the ends of each of the resistors, A, B, and C. A, B, and C can be measured by placing a voltmeter across the ends of each in turn. Okay, we have 3 resistance rings, and after each of them we're measuring how much was lost. The total potential difference across the 3 resistors will be 9 volts. We're saying we're losing 3 at C, 2 at B, and 4 at whatever one, and these are 9. Okay. It's just addition. Okay. And this in fact will be the reading of voltmeter when it is placed across the terminal of a battery X and Y. Okay, X and Y, that is our battery. The total potential difference across the 3 resistors will be 9 volts lost. And this in fact will be the reading of voltmeter when it is placed across the terminals of a battery X and Y. Is the current flowing that way and that way, and they're measuring at both sides. And with one side it comes with full and the other one with 9 minus. If now the switch is opened, the voltmeter across X and Y will read 10 volts. If it's opened, 10 volts. Because we're coming 10 volt less, the reading informs us that the electromotive force of a cell is 10 volts. So it presses from A is, so I think A is the why is the battery now X and Y? I think the current comes from A. A is our giver of our current. And it presses onto Y, onto the battery with 10 volts. And if we close on the switch, then it must be 1 volt there. 9 were from the resistors in the other circuit. Take away. Its total available voltage. When this EMF, electromagnetic force, no, it was something else. It was the electromotive force. Electromotive force. When this electromotive force is applied to the circuit, the electromotive force causes a potential difference to be set across each resistor in the circuit. Causes a potential difference to be set up across each resistance circuit. And these potential differences total 9 volts. You may realize that 1 volt seems to be lost when the electromagnetic force of the battery is employed to drive a current around the circuit. This lost volt is a part of the electromotive force, which is required to overcome the internal resistance of the battery itself as the current flows through it. Now, we don't have time left, and we have to protect intervention. Now, we're going to continue in the next part. Basically, we're saying something like we're measuring how much is lost in current that flows through the resistors or the other way around. And that was the electroengineering part, I think, wasn't it? If you were here for electroengineering, you can go directly to the next part of electroengineering. We will do... Where are we Leg injury prevention training. If you still participate in the leg injury prevention training, it's better to honors. Good standing leg, the other leg in the air, and we're swinging it with the flex foot to the side and front. Now with the other foot to the side and front. And the other foot in front and back. And the other leg in front and back. And now pine pad crawl. Bring our leg up, breathe in. Out leg to the side. Again in. Out into the middle. And down. Other leg up, breathe in. Out to the side. Again in. Out into the middle. And down. And again a leg up. Also arms out. And go on with the arms over to one side. Over to the other side. To the middle. And now leg also over to the other side. And change. And down. Now the other leg up. And arms out. And to one side. To the other side. And cross. And in the middle and down. And now one leg up and press with the leg up and to the side. And the other leg up and press with the leg up to the side. And now next exercise, we can go a bit onto the knee. Stand on one leg, turn over to that leg, go down with the knee, turn to the other side, and come up. Then around, stand, turn over to that leg, go down, turn to the other side, come again up. Now with your leg, stand, turn over to that leg, go down, over to the other side, and come up. And then around, stand, turn over to the leg, go down, the other side, and up. Another clockwise can go again onto the knee. So stand with one leg and go always in 90 minutes intervals, 7 clocks times. And the one here also. Now with the other foot, 12 o'clock, and we get to 1:30 and to 3. We get to 10:30 and 9, and we do 7:30 and 6, and also having that not done 4:30 and 3. And now the pipette with standing leg, the other leg with the heel on the ground, lift the heel off the ground and place it again on the ground. Other leg, heel onto the ground, lift the heel off the ground and place it again on the ground. And now next exercise, one hand on tummy, one on lower back, lift the leg up in a straight line. If the quad muscle is cramped, then bring the leg up and point the foot down. So leg up, flex foot, try to bring the leg higher. And bring it now up and point the foot down. And the other leg, bring it up in one straight line as high as possible. Control with the hands, but you don't fall back. Try to move the leg higher. Bring the leg up and point the foot down. And now the stamp, leg up and down, and down. The other foot. And now the horse, leg in and out, in and out. And with the other leg, in and out. And now you can continue with the stamp of horse or make a rest, or you do the camel, the whole body goes also down. And last one, and with the other leg. And now you can do a rest, horse, camel or stand, or you do this one. Whole leg swings, leg is straight, flexed foot. Try to be taller up with the standing leg, try not to fall in the other one. And with the last one, and with the other leg. Taller with the standing leg. Try not to fall in the downward flex foot at the swinging leg. The other part of our body comes to the normal down when the swinging leg comes up in the last one. And now with trunk, you can light our legs to the side. Breathing out. Breathing out. Good. Breathing across the legs. And breathing out. It was bad. Lekker je wünschen. I thank you very much and until next time.